Good morning. In this class, we will discuss about examples for differential aeration corrosion. Actually, electrochemical corrosion can be classified into two categories. One is galvanic corrosion and one is differential aeration corrosion. In this class, we discussed examples for differential aeration corrosion. First one is pitting corrosion or localized corrosion. Second one is crevasse corrosion. Third one is pipeline corrosion. Last one is corrosion on wire fence. These are the examples for differential aeration corrosion. First one, pitting corrosion. Pitting is a localized attack resulting in the formation of the pit or hole around which the metal is relatively unattacked. This is a diagram for pitting corrosion. So, water droplet is located at a single space. Automatically, it creates the hole. Example: metal area covered by a drop of water, sand, dust, scale, etc. Let us consider a drop of water or aqueous sodium chloride resting on a metal surface. The area covered by the drop of water acts as a anode because less aerated part. So automatically corrosion occurs. The uncovered area, that means freely exposed to air, acts as a cathode due to high oxygen concentration. The rate of corrosion will be more when the area of cathode is larger and the area of anode is smaller. Therefore, more and more material is removed from the same spot. Thus, a small hole or pit is formed on the surface of the metal. At the anodic part, iron is oxidized to iron oxide. At cathodic part, hydroxide ion formation. So, Fe2 plus ion combined with OH minus ions to form rust. Then second one is crevasse corrosion. If a crevasse between different metallic objects or between metal and non-metallic material is in contact with the liquids, the crevasse becomes the anodic region and suffers corrosion. This is due to the less oxygen in crevasse area. The exposed area acts as a cathode. So this is the diagram for the crevasse corrosion. Less aerated part acts as a anode, more aerated part acts as a cathode. So in the less aerated part acts as a anode, that means corrosion occurs, rust formation. Third one is pipeline corrosion. Differential aeration corrosion may also occur in different parts of the pipeline. Less aerated part, then more aerated part. So less aerated part, that means clay area. More aerated part, sand area. So less aerated acts as a cathode. More aerated acts as a anode. So the more aerated part undergoes corrosion process. Buried pipelines or cables passing from one type of soil to another, say from clay, sand, may get corroded due to the differential aeration. And last one, corrosion on wire fence. Corrosion on wire fence, a wire fence in which the areas where the wires cross and less aerated than the rest of the fence, and hence corrosion occurs at the wire crossings which are anodic part. In this diagram, crossings or act as a less aerated part. Less aerated part act as a anodic part. Then, so it undergoes corrosion process. More aerated part act as a cathodic part. So no issues. Other examples for differential aeration corrosion. First one is corrosion occurring under metal washers where oxygen cannot diffuse easily. Lead pipelines passing through clay to cinders undergo corrosion. Since the pipeline under cinders is more aerated, it gets corroded easily. Then factors influencing the rate of corrosion. The rate and the extent of corrosion mainly depends on nature of the metal and the nature of the environment. First one is nature of the metal. Position in EMF series. When two metals are in electrical contact, the more active metal, higher negative reduction potential undergoes corrosion. So the extent of corrosion depends on the position of the metal in the EMF series. Metals above the hydrogen in EMF series get corroded vigorously. Lower the reduction potential, greater is the rate of corrosion. Therefore, the rate and severity of corrosion depends on the difference in their positions in their EMF series. Then relative areas of the anode and the cathode. The rate of corrosion will be more when the cathodic area is larger. When the cathodic area is larger, the demand for electrons will be more and more. This results in an increased rate of corrosion. Then purity of the metal. 100% of the pure metal will not undergo any type of the corrosion. Then over voltage or over potential. The nature of the surface film. The nature of the corrosion product. Thank you.